Welcome back. This is 6.2.2.2. In this section, we're examining how the DTFT is related to DTFS for a single period or periodic sequence. Let's see what we are talking about. Given a periodic sequence of n samples, let us now extend it to 9 samples and keep on extending it for larger and larger periods, maintaining the on periods or the on samples to be the same. That means all we are extending is the silence. When n tends to infinity, then we are back to an aperiodic sequence. In this aperiodic sequence, we can take the DTFT, and this is the equation for the DTFT. Notice that although we are taking from n equals to negative infinity to infinity, in reality we are only taking the on sampled period. The samples that are 0, even though we are taking it in this equation, is of no use. Therefore, in this particular example, we are only taking from n equals to -1 to +1. Now, let's be clear. This is the DTFT of this aperiodic sequence, and we need to plug in different omega from minus pi to pi or from 0 to 2 pi continuously. So that means we substitute different omega and we compute this. And this is computable because n is only from -1 to 1, and therefore this will converge to some value. Now, let's then study this equation for the DTFS. To take the DTFS of the period 6, then we plug in this equation, ck equals to 1 over 6 for period 6, and then we do a sum of n samples. And here typically you go from 0 to n-1. But now I introduce the notation. What we are saying is that actually for DTFS, you can take any n sample period. It does not need to go from 0 to n-1. So in this particular example, it is better for us to take from, let's say, -3 to 3 or -3 to 2 for one 6 sample period. And of course, when we extend to 9, well, it goes from -5 to 4 or whichever, but the only non-zero samples are still the same. So this notation of bracket n is a better representation for us to understand this DTFS equation. We should take the appropriate n samples such that in this example, it clearly shows that there is no change even though n goes to infinity because only zeros are padded. And therefore now we see that this equation over here of n sample, regardless of what n, is actually equivalent to this one because only there are 3 non-zero terms here. So actually, once you realize that, then isn't it obvious that when we move n across here, is nck is equals to this particular equation, and this particular equation is the DTFT of the aperiodic signal for the correct omega. Okay, so we have to go and of course choose what omega we want to use, and the DTFS is always 2 pi over n times k, and in DTFT omega is continuous. So this diagram shows the relationship of DTFT and DTFS. So nck is actually the DTFT values at this particular frequency, 2 pi over n times k. So this is explained in more details in the next slides. The other way to look at it is this. X omega at this particular frequency, 2 pi over n times k, is actually n times ck. So if you calculate CKs, all you need to do is to multiply by n and you get the value. So what does this mean? Well, let's take a look. For this aperiodic sequence going from 0 to, let's say, whatever, and only these few values are on. Once we take the DTFT, we can plot from, let's say, 0 to 2 pi. And this is the DTFT of this aperiodic sequence. Let us now repeat this aperiodic sequence periodically. In this example, it repeats every, how many samples? 8 samples. This is 8 samples. In this, every 16 samples. In this, every 32 samples, it repeats. Well, let's see what happens. If we take the DTFS of this, we get the CKs and we multiply the CK by n. In this case is 8. In this case, NCK, n is 16. And in this NCK, this n is 32. So we calculate the CKs for different values of n and we multiply it by that. You will see that we get the CKs. And you realize that the blue lines, which represent the NCKs, are meeting the green line, which is x omega, directly. So they are the same values. And as n becomes more, basically we get more lines. And why is this so? It's because we are actually sampling 2 pi over n times k. So as n becomes small, 2 pi over n becomes smaller. So we are introducing higher resolution along the horizontal axis of omega. Okay, so therefore in this example, k equals to 0 to 15, and here is the next example is 2 pi over 32 times k equals to 0 to 31. And so you see actually more and more lines here. But these more and more lines, when we multiply n by ck, is actually this blue line. And of course, when n goes to infinity, it becomes the green line, which is the continuous function. Okay, so to repeat, there is a deep relationship between the DTFT of a single period of a DT of a periodic sequence. And this is the relationship. Thank you.